Okay, well, we'll keep rolling and do a shear video now. So let's talk about shear and why we have shear reinforcing. So one of the cool things about concrete is it's very weak in tension, fairly strong in compression, and then kind of in the middle in shear. And if you take a stress block and look at the shear forces on it, and rotate it 45 degrees to its principal stresses, what we find is we have compression in one direction and tension in the other. And that's why shear failure in concrete is actually a tension failure in from a mechanics point of view. Here's a little beam photo for some testing. You can see the load here is applied pretty close to the end, and it just kind of destroys that intersection of the web there. Here's another picture. You can see there's some tension cracking in the concrete. These stirrups are quite tight together and provide a lot of strength. Without those stirrups, obviously, that wouldn't quite be there. Okay, so the mechanics of shear, we get some friction in the compression zone, some aggregate interlocked, and then dowel action at the bar. And then if we add reinforcing still, we get a tension force in each bar that basically equates to shear strength. Okay, so some fundamental relationships. We want the nominal shear strength, so V sub n times phi, to be greater than the shear demand. So the shear demand is going to be calculated from a beam analysis. The shear capacity is going to be calculated based on the mechanics of the concrete and the rebar stirrups, or ties if we happen to be in a seismic area. So this nominal concrete or shear strength is a function of the concrete shear strength plus the still shear strength. So we will calc both of those separately. And then there's a limit on the square root of the compressive strength. We need to keep it under 100 psi for these equations to hold valid. Okay, so I'm going to skip some of this. You can read that, some different reinforcing types. So this is where the rubber meets the road. If we have shear and flexure only, so this would be your typical beam. Our concrete component of shear strength is 2 square root F prime C beam width. BW is the beam width, or the web width, really. So in a tapered girder like you might have on a highway, that would be the width of the web portion times D, which is from the extreme compression fiber to the tension reinforcing. If we have axial compression, we have actually an increase in the shear strength because of the compressive force, which is pretty cool. And then if we have axial tension, the concrete shear component is 0 because the bar is being pulled, or the concrete aggregate and cement is being pulled apart, and really doesn't have the juice to do a whole lot of good for us. Okay, so spacing requirements and steel requirements. If we start near a low shear area, if the shear demand is less than phi times the concrete strength of shear divided by 2, we don't need stirrups. I can't handle that because a lot of the design I've done is more in seismic areas where we would have to put stirrups anyway. But per the code, in non-seismic areas, we can omit some stirrups. And there's a region where we have kind of the edge of this to up to the phi concrete shear strength portion, where we're going to have stirrups at least D over 2 spacing, or this limit excuse me, of 24 inches. Okay, and then if the phi VC is less than the shear demand, which is often the case, then we're going to place the stirrups at least D over 4, where D is the distance from the bar to the edge of the concrete. And then we'll decide where we, the size of the stirrups based on strength. Okay, so let's jump into shear reinforcing strength. So there's a shear reinforcement minimum area, so that's what this equation is. You can get into that a little bit more. There's a spacing requirement, which we just talked about. And then the steel strength for shear reinforcing is given by this relationship. So the area of the shear steel. So normally we're going to take the area of one bar times 2 because there's generally two stirrups, one on the near side, one on the far side, times the yield strength of the stirrup times D, and then divided by the spacing. And that gives us our steel strength, and then there's a limit, an upper bound limit on how much reinforcing we can have, or shear reinforcing. Okay, once we have that, we can add the two together. That gives it for an inclined situation. Where is that? I guess I'd have to go back here. Hang on a sec, let me go find that. Okay, so once we have the steel strength, the concrete strength, we can add them together, multiply by 0.75, compare that to our demand, and then we're good from there. Okay, so let me just see if there's anything else worth looking at, talking about. There's a little bit of preliminary design help for you. And then an example of the reinforcing layout as it might vary in an actual beam. So at the end of the day, we're going to want to schedule this, and let's jump over the example and see what that looks like. Okay, so this is actually what we were just looking at. You can see I've called out number 4 stirrups at 10 inches on center, and that would have to meet D over 4, so that's a fairly deep beam. And then here I didn't call it out, so that would be helpful if I were to do that, and then in the middle there isn't any. So let's go ahead and back up into this example for shear. So all of the examples that are typed out like this will start with how we got the shear demand VU. And this is important. You can't just pull it out of the hat. It doesn't come out of a book. You need to calculate it based on the applied loads to the structure and a good healthy beam analysis where we're calculating, in this case, shear. And in concrete, we actually need to know the shear variation along the length of the beam, as we saw. In steel and timber, not as much, because usually the sections are the same along the length of the beam. Okay, so the step 2A here, we're calculating the concrete shear capacity, and we find that our shear strength is less than the demand, which is not a big surprise. That's usually how it is. If we look at this figure, you can see the shear varies along the length like a normal shear diagram. And so at some point, the shear may be low enough that we can go to a different spacing of the stirrups. Okay, so once we have that, we can calculate how much required shear strength do we need out of the steel. So that kind of helps us just get a feel for what we're going to need. And then at some point, we're going to calculate the contribution of the stirrups we chose. So it looks like here we're trying 2 number 4 bars, which is basically one stirrup, a bar on the near side and the far side of the section. 0.2 square inches is the area of a number 4. It's greater than our minimum, and then we plug that into our steel shear strength equation. We get 65 roughly kips. We can't go over 76. I guess there's a limit if we have to cut the spacing in half. and that's at 76, so we're okay there. And then here we add up the concrete component and the steel component, get 102.6, multiply by 0.75 phi factor. We get 77 kips, which is greater than our shear demand, which we could go back and look at that if we needed to. Then there's kind of a discussion about where to start and stop the stirrups. I'll let you get into that. And then at the end of the day, we have a diagram that looks like this. Would be nice for me to call out the spacing there, just to be thorough. Okay, I think that's it for this little video. Hopefully it helps you get a leg up on stuff, and we'll talk more, as always, in class the next time.